Hello everyone, today I'm going to introduce solid polymer electrolytes for solid-state batteries. As technology advances, electric vehicles are becoming more common. To improve battery energy density, new materials are needed, and lithium metal is a promising anode candidate. However, lithium metal is incompatible with liquid electrolytes. During charging, it can form dendrites, which create serious safety risks because liquid electrolytes are volatile and flammable. For this reason, solid-state batteries, which use solid electrolytes instead of liquid ones, have attracted significant attention. Why do we choose polymers? Solid electrolytes can be broadly classified into two types, inorganic and polymer. Inorganic electrolytes generally offer higher ionic conductivity, but their rigidity often results in poor interfacial contact with the electrodes. In addition, cracks can form because they cannot effectively accommodate the stress caused by volume changes during charging. In contrast, polymer electrolytes are soft, flexible, and easy to process, allowing better contact with the electrodes. These advantages make polymers a promising choice for solid-state batteries. Ion conduction in polymers mainly occurs through three mechanisms. First, when lithium salt dissolves in the polymer, lithium ions coordinate with polar groups such as ether-oxygen, forming temporary cross links between chains. The polymer segments then undergo snake-like motion by thermal vibration, allowing the ions to repeatedly coordinate and dissociate as they move over long distances. This process is called segmental motion and mainly takes place in amorphous phases. Second, in mixed amorphous crystalline systems, ion transport can occur along the crystal surface through surface coordination, known as surface diffusion, while the intercrystalline regions hinder transport because the polymer segments are immobilized. Finally, in well-defined crystalline complexes, ions can move by hopping between adjacent sites. The molecular weight of the polymer and the type of lithium salt are therefore important factors, since ion hopping depends strongly on accessible defects in these crystalline polymers. Solid polymer electrolytes are formed by dissolving ionic salts in polar polymer hosts that can coordinate with the ions. Polyethylene oxide was the first polymer widely used for this purpose, although many other polymers have since been explored. The formation of polymer salt complexes depends on the balance between solvation energy and lattice energy, and stability improves when both the polymer and the salt have relatively low lattice energy. In addition, mobile anions can cause self-discharge and degrade the electrode surface, reducing device performance. Therefore, salts with large organic anions, such as LiTFSI and LiTFSM, are often preferred. Solid polymer electrolytes still face several challenges. Most require moderately elevated temperatures to achieve high ionic conductivity. For example, PEO-based electrolytes typically operate at 60 to 80 degrees Celsius. Improving room temperature conductivity usually involves increasing the amorphous content and lowering the glass transition temperature. But a lower glass transition temperature often weakens mechanical properties. Molecular design of polymers is one strategy to reduce this trade-off. Another challenge is the low lithium-ion transference number, which leads to dominant anion transport and uneven lithium deposition. One important research direction is therefore to immobilize anions on the polymer chains. In addition, high interfacial impedance between the electrodes and electrolytes, as well as a limited electrochemical oxidation window for high-voltage cathodes, remain important issues to address. Thank you for listening. Wish you have a good day.